Okay, welcome to lecture here. We get started in just a sec, continuing on chapter 13, and then I think we'll get into 14 after that. And the notes again are up on Canvas if you need them. All right, so we been talking about equilibrium problems and problems where we're not given equilibrium conditions, but are asked to solve for the equilibrium concentrations of everybody. To do that, as we talked about last week, we do need to do an ice table. The ice table represents initial change in equilibrium. And basically, the initial is pretty much what it sounds like. You put the initial concentrations in to a table. If you're just given the reactants and nothing about the products, you could assume that the products are zero. You could also assume that the reaction is heading towards the product side. Um, and that's important for the change part. The change part we represent usually with an X. And we also take the coefficients in the balanced equation. Again, by doing so, that takes care of all really the stoichiometry, the mole to mole relationships that's happening. So, for example, if the coefficient on the reactant side was, say, 2A, when we get to the change part for the A, it would be minus 2x and so forth all the way across. When you get to the product side, since they are gaining in concentration as the reaction takes place, we represent those with pluses. So like plus x on that side, plus 2x. Again, whatever the coefficient may be. When you get to the equilibrium line, you basically just carry everything down. So you take basically the initial and then the change line together. So initial minus say 2x or initial plus x or something like that if you're on the product side. We then put that stuff into the equilibrium line into the equilibrium expression, and we essentially solve for x. And when we solve for x, there's a couple of different ways that we've seen so far to sort of solve for x. Maybe it's a quadratic type equation where you'll get two x values. Maybe it's a sort of perfect square in that situation. But however you need to do it mathematically to solve for x, you solve for x. When you do that, x that you get is all the x's in the table. So you essentially could go back to the equilibrium line and put the x in for everybody, and that will give you your equilibrium concentrations for all the species that are present. Now, since it's sort of math and everything like that, as we talked about as well last time, if you do have some time when you're done with the problem, it's probably a good idea to perhaps put those equilibrium values you got back into the expression. And if you do, you obviously should get the same value or pretty close to the same value as the equilibrium constant. So it's a good way you could kind of check yourself again to make sure that nothing went wrong with the calculation part. As we saw, I think the very last one we did was a pretty entailed or detailed type of quadratic one with a lot of foiling, factoring, putting things together. And it's very common people sometimes mess that part up, especially when they're maybe copying something over or something of that nature. All right, I think that's where we sort of left off. Any questions on any of that stuff there? Okay, so I think we left off with this example here. So why don't you take a few minutes here, start working through it and see where you get to, how you're working it, and then we'll talk about this particular problem here. Okay, so let's take a look here. So again, we're given, in this particular case, we're given pressures here, and we're looking for the pressures of everybody at equilibrium. So we have the pressure of N2, we got the pressure of H2. And as we talked about, I think last week as well, you can do these ice tables in concentrations. You could also do them in pressures, so they work the same way. If you do have to do it in pressures, though, since we're doing a problem like this, it does need to be usually in atmosphere. So I think we probably covered that earlier on in this chapter, but just to remind you that when you do an ice table, the units do have to be atmospheres if you're dealing with pressures. Even in a problem where they give you the pressure, say in torr or something like that, and they ask what are the pressures in torr, you do have to actually convert the pressures from torr to atmospheres, do the ice table, and then convert it back to torrs at the end. So I've seen problems like that where I kind of give you everything in torrs, and they're like, hey, what's the pressure in torrs? And people think they could just kind of plop it into the ice table in torrs. But you do actually have to convert it to atmospheres, do the ice table, and convert it back to whatever unit you're looking for. Works the same way, and that's why, again, here we're not given a Kc value, but we're given a Kp value. But basically, you approach it the exact same way. So really, instead of a Kc expression here, what we will be dealing with is a Kp expression. So the Kp in this case would be the partial pressure of NH3, and we do need to cube it because of the coefficient, divided by the partial pressure of N2 times the partial pressure of H2, which would also be cubed. I'm sorry, not cube the top guy, square the top guy. There we go. Square the top guy and cube the bottom guy. And that would equal our 4.31 times 10 to the minus 4. So really, you're just going to kind of approach the same way. Concentrations, pressures, all kind of works the same way in the ice table. So let's take a look at what the ice table will kind of look like here. So here we would have initially 0.862 atmospheres. This would be 0.373 atmospheres. And again, we weren't given any pressures for our product side, so safe to assume that it is 0 on that side. Change is going to be, again, since it is 0 on the product side, safe to assume this reaction is probably heading in this direction towards the product side. So that means our reactants should get smaller. So this is going to be minus x, minus 3x, and plus 2x. And that means at equilibrium, 0.862 minus x, 0.373 minus 3x, and 2x. Any questions on the ice table or how it's set up? So again, you can kind of see it's the same deal, even with concentrations, pressures, all works the same. In addition, at this point, what we're going to do is put those guys into our Kp expression that we had written there on the previous slide. And if we put that into our Kp, we will get that our Kp value was 4.31 times 10 to the minus 4 equals our products, which is 2x. And again, we do need to square it, divided by our 0.862 minus x, and our 0.373 minus 3x. And again, we need to cube that thing. At this point, we could factor out, do some crazy math, but I don't know if we really want to do that because that's a lot of crazy math, and I don't have a lot of screen here left. So what we can do is look at a couple of things here when we do a problem like this that might help us out. First off, when we look at the K value that is here, so when we look at this K value, this K value is a relatively small K value. So remember, anything sort of less than 1 is relatively small. And since it's relatively small, what that means is when this reaches equilibrium, as we've talked about before in this chapter, we should mainly assume that we have reactants present, right? So small value, we should mainly have reactants probably present at equilibrium. And if we have reactants present at equilibrium because of the K value, that probably means that this number here, which is our X's, are going to be relatively small. So the change here is probably going to be relatively small. And what that means is we could actually make an assumption that X will equal 0 in this particular case. So we could assume that X will equal 0 in this case because X, which represents the change part, should be relatively small because of the equilibrium constant value. Now, clearly we cannot get rid of all the X's in this thing. Otherwise, we have nobody to solve for. So that's not going to be very helpful. So in terms of the X's that we could get rid of, it really is just the X's that you're going to subtract something from or add something from. So it is really those X's there that I really badly just scribbled out there. Try to get rid of that. Try that again. It is really the X's here that we're going to add or subtract somebody from. So it really will be just those two X's. We need to leave this X still there so we have something to solve for. So when we make the assumption, again, like I said, you can't get rid of all the X's. It's just the X's that we're subtracting from. It's the X's that we might be adding something to. And if we do that, that will make this a little bit more easy, hopefully. That will give us still 2x squared up on top. And this then will become 0.862. This will become 0.373 cubed. And that looks a lot easier perhaps to solve than what we had up on top. So if we go to solve this, we want to basically clean up the stuff on the bottom right there. So we're going to take 0.373 and cube it. We're going to times it by 0.862. That gives you 0.0447. And then I'm going to multiply that to the other side. So 4.31 to the minus 4. And if you do all that math, again, clean up the bottom here and then multiply it to the other side, you get 0.00001928 equals 4x squared. I'm going to divide by 4 and then take the square root. Divide by 4 and little square root action gives us an X value when it's all said and done of 2.20 times 10 to the minus 3. Any questions on that so far? So because we have a small K value, we can make an assumption that the change is going to be relatively small, and thus X will be relatively small since that represents the change. Again, really only the parts that you're going to subtract off it from a number or add to a number. But once you do make the exception or the assumption, you do need to really kind of check to make sure that the assumption is okay. And the way that we check to make sure the assumption is okay, there's a couple different ways, but in here we'll use the common rule, which is sometimes referred to as the 5% rule. So we'll use what is known sometimes as, as the 5% rule. And the 5% rule means basically you take the X value that you just got. So you take your X value, which we had on the other page, 2.2 times 10 to the minus 3. And then you basically divide it by what you were going to subtract it from. So in one case, we had 2.2 times 10 to the minus 3 divided by 0.862. Again, that's what we were going to subtract it from. Times it by 100%. And if you do that, your calculator doesn't die on you. There we go. 0.255%. And that is less than 5%. So this is a good assumption. You could actually do it for both. In my experience, if it's good on one, it's probably good on both, but you technically could take, say, 3 times 2.2 times 10 to the minus 3 and divide it by 0.373 times 100%. And you will get not the same answer, but you'll get the same answer in terms of it should be okay. And again, if you do that, you got something like 1.8%, also less than 5%. So still good. So you could check them both if you like. Like I said before, sort of in my experience, if it's you checked one of them and it's good, there's probably a pretty good chance they're both good or whatever it may be. So usually you don't run into too much problems like that. Now, if it was more than 5%, what that means is you do need to go back and solve it some other way. For our purposes, that would probably be something like the quadratic formula. You would need to go back and solve it. But you could definitely try this little rule here because it will kind of help you out. So since our assumption is good, that is going to be our X value. That means that the pressure of N2 would equal 0.862 minus 2.2 times 10 to the minus 3. And that would get us 0.860. And again, this is not a concentration, but it is a pressure. So it gets the units of atmospheres. Our partial pressure of H2 would equal 0.373 minus 3 times 2.2 times 10 to the minus 3. And that gets us 0.373 minus 3 times 2.2 minus 3. 0.366, it looks like. And again, atmospheres, since it's a unit of pressure. And lastly, the partial pressure there of NH3 equals 2 times X, so 2 times 2.2 times 10 to the minus 3. Looks like 0.0044 atmospheres as well. Question on that, again, you could take those numbers like we talked about before, you could put it back into the expression, and again, you should end up with the pretty close to the exact same K value as we started with. And if you do, I believe you do end up with K value that's very close to it. Questions on that particular one there? So this is another way that you can solve an ice table. So the question is, why did we not do the assumption on our previous problems? And the reason we did not do the assumption on the previous problems is if you looked at the K values on the ones we dealt with earlier, I think we had a K value of 7. We had a K value of 54.3. Those are considered, again, a large value of K, which means because they're a large value of K, we would expect a lot of products at equilibrium. And that means that the change part should be relatively sufficient there, are pretty big. So we cannot do the assumption. So again, you can only do the assumption when your K value is less than 1 or a small value of K, and you should check it because it will not always work or be good to do. So you should always definitely make sure that you check it and not just assume that it will be good, because it will not always be good. Any questions on ice problems, equilibrium problems? We've now seen a few different ways to solve these. Again, quadratic, assumption, perfect square. And these will typically for our class be the ways that we will solve these type of problems. I will say that there's another common way that sometimes people will solve these type of problems, and we will not do it that way. And that's what's referred to as successive approximation. Successive approximation, if you kind of don't do it very well, you might be there all day doing it. But the idea behind sort of successive approximation is, well, I know my X value needs to be less than this number. So what I will do is just pick a number that's less than it and put it in. And I'll put it into here and here, and then solve for X. And when you solve for X, you may get the same number as you put in. And if you didn't, then the number that you get for X is the number you put in. And you keep kind of putting an X value in until the number you put in and the number you get out are essentially the same number. And then you'd have sort of successive approximation. Again, could take a very long time if you're not very good at it and stuff like that. So we will not have any problems that you'll have to solve that way. So the most difficult way will be probably quadratic formula. But in case in the book, sort of a solutions manual or something like that, again, that's a very common way. Sometimes people will solve these type of problems is through that successive approximation, which again, may not go good for a lot of people if you don't do it very well. Any questions on how to solve any equilibrium type problems or anything like that? Okay. So the last thing we're going to talk about then in this chapter is Le Chatelier's principle. So let's talk a little bit about that. So basically the idea behind sort of Le Chatelier's principle is you have a system that's at equilibrium. So you essentially have this system that's at equilibrium. So again, you have something kind of going back and forth at the same rate, and it's all happy, it's going back and forth. But then you do something to the equilibrium to mess it up. So you add a stress, as sometimes referred to. So you add a stress to the system that's at equilibrium, and it's basically going to mess up the equilibrium. And what's going to happen is once you sort of mess up the equilibrium, it's going to want to try to get itself back to the equilibrium sort of condition. So it's going to try to get itself back to that equilibrium condition. And it will need to do that by either three options, either kind of shift to the right, which basically means we need to make some more products. May have to shift to the left, which means to reach equilibrium, I need to make some more reactants. Or there may even be a situation where even though you did something to it, there may have really no change that will occur, even though you sort of did something to it. So what are some stresses that we commonly sort of talk about when we have a system at equilibrium? When we talk about things that are stresses, that is concentration. So we either can increase the concentration, remove the concentration. When we talk about volume and pressure, those guys are usually related to each other. So volume and pressure dealing with gases is something that we can kind of do to the system, either increase or decrease both of those, increase the volume, decrease the volume, increase the pressure, decrease the pressure. Temperature is another stress that you can apply to a system. So either we can increase the temperature, lower the temperature. And lastly, a catalyst, which as we talked about in the previous chapter, something that you typically add to a reaction to speed it up. So that's another sort of situation that you can sort of add. So let's talk about some of these effects. Let's first talk about concentration. And concentration, all right, so let's talk about concentration. So when we have concentration, basically there's two things that you could do. You can either add more concentration or you can remove concentration. So the idea with concentration is if we add more, it will shift the equilibrium away from the side we added it to. So when you add, it goes away. A good way to remember that, add away. And basically, if we remove, which is our other option, it will shift towards the side we removed it from. So when you add, it goes away. So what that means is if you add more reactants, it will shift to the product side. And if you add more products, it will shift to the reactant side. And same thing with removing. If we remove reactants, it will come towards the reactant side. And if we remove some products, it will come towards the product side. So you could kind of think of this like when you have somebody kind of like on a seesaw, if you will. So if you have, and we'll call this side the reactant side, this side the product side, and this guy's at equilibrium at this point. And let's just say that we added somebody to the product side. What's going to happen when we do that is we will get this situation. Stick figure 101. Here we go. And obviously in this case, what happened is we put more people on the product side. So to fix that, we need to actually have more people hop on the left-hand side. So it is going to shift equilibrium this way. And when we do so, we will once again sort of return to equilibrium here. And we're back to equilibrium number 2, if you will, from equilibrium number 1. So we had a system, we added more products to fix it. We needed more reactants to reach equilibrium. And again, we return to equilibrium. Same thing happens if we sort of remove. So if we started with our same guys here. And we're at equilibrium again. On the left here is our reactants. On the right is our products. In this case, let's just say that the guy on the right hopped off of it. When he hopped off of it, it's going to crash down like so. Again, making this guy unhappy. To fix that, we need to put more people on the right-hand side. So it's going to shift to the right. And when it does, we will end up back at equilibrium once again in this case. So again, when we remove, it goes towards the side. We removed it from. When we add, it goes away from it. Any questions on concentration? So when we talk about concentration and adding and removing, adding is pretty simple. If I add something, I pretty much could just pick it off the shelf and dump it into the beaker and so forth. Now, if I want to remove something, how do I remove something that's, say, in a solution? Do I just reach in and grab it? The answer should be no. You shouldn't reach into a solution, right? So if I have a solution, which is pretty much, ions floating around in it, and I want to remove something, I can't just like physically reach in there and grab something out. How would we possibly remove something from a solution? One common way is to add something that makes a precipitate. So if you add a reagent to that solution and it makes a precipitate, obviously that is removing something from the reaction. Remember that a solid is not part of the equilibrium. So when you do that, it will essentially be like you reached in and took those ions out of the reaction by adding a precipitate. So that's a very common way that you can sort of remove something from a solution. Another very common way that you can do it that you won't kind of physically see it. So obviously if you made a precipitate, you would be able to really see it. Another common way is to make water. So if you have a equilibrium that has H plus in it or an equilibrium that has OH minus in it, and you add something that actually forms water, it is like removing either the H plus or the OH minus from the reaction. And again, you won't be able to physically see that like, oh, I made water, but the formation of water is another way. Again, water, which is a pure liquid, will not be involved in equilibrium either. So those are two very common ways that you can actually remove something from the equilibrium and either make a precipitate or a water. Now, another important one is temperature. And when we talk about temperature, temperature works the same way as concentration, and temperature is really dependent on what type of reaction is happening here. And what type of reaction means, is it really exothermic, which means heat and energy is released, or is it endothermic, where our heat and energy is absorbed? And usually the most common way this is sort of displayed in a reaction is they will give you the delta H value. And again, if the delta H value is negative, that is exothermic. And if the delta H value is positive, that is endothermic. So when we look at a reaction and we decide it is exothermic, what that means is when we look at the reaction, we would add the heat or energy to the product side if it's exothermic. It is thought of as being a product, while if it's endothermic, the heat and energy would be considered a reactant and be added to the reactant side. And basically, temperature works the same way as concentration. So if we increase the temperature, it will shift away. And if we decrease the temperature, it will shift towards. So temperature, same way as concentration. The important part is to try to determine whether or not it is exothermic or endothermic. And so if we have a exothermic reaction, and we increase the temperature, that would be like adding more heat, so it should shift to the left. If we decrease the temperature, that would be like removing the heat, and it should shift to the right. And vice versa for our endothermic. If we increase the temperature of our endothermic, it's like adding more reactants, so it should shift away. And if we decrease the temperature, it's like removing our heat on our reactant side, it should shift towards it. So again, the important part about temperature is you need to determine whether or not it is endothermic or exothermic. And then it basically just works the exact same way as concentration. Add away, remove, come towards. Question on temperature change. The other thing that's important with temperature is, as we talked about, it is the only thing that will affect the actual value of the equilibrium constant. So if you have an equilibrium constant at 25 degrees Celsius, and let's say it's 100, and you raise the temperature from 25 to 50 degrees Celsius and it's 200, they will have different K values at those two different temperatures. But again, if you keep it at 200 all the way through, it should maintain this K value. Keep it at 25 degrees all the way through, it should maintain it. But the difference between the K value at 25 degrees and 50 degrees, those two values will be different values. Any questions on temperature changes? Okay. The last sort of effect is pressure, and really pressure and volume are oftentimes tied together, pressure and volume. And they're tied together. If you think about in Chem 50, a good thing about a gas law that involves pressure and volume, that is like your P1 V1 equals P2 V2. That's our good friend Boyle's law. And if you remember Boyle's law, there is a relationship between pressure and volume, and this would be at constant temperature. So as the pressure goes up, volume goes down, and vice versa. As the pressure goes down, the volume goes up. So when we're dealing with pressure and really pressure and volume, it usually is involving equilibrium that involves gases. and you can look at either one of them. I personally think when you have sort of a pressure volume type situation, volume is kind of the easier one to sort of think about. So if I increase the pressure, what's going to happen is the volume is going to go down. And as the volume goes down, what we want to do is we increase the pressure. So pressure went up. So we kind of want to bring the pressure back down. So to bring the pressure back down in a situation where we have a very small volume, we need less gas molecules in that small area. So when we increase the pressure and we decrease the volume, what's going to happen is it's going to shift to the side with less gas molecules. So whichever side has the least number of gas molecules will be the side it will shift to. And clearly that is reaction dependent. You have to look at the reaction, look at everybody in the reaction that has G's next to them, and count up sort of the coefficients to figure out how many gas molecules you have on each side. And then whichever one is the smallest, you will shift it that way. And the opposite is true. If we decrease the pressure, the volume will go up. So we brought the pressure down, the volume went up. We have a larger area for the gas molecules to fly around in. So since the pressure went down, we kind of want to bring the pressure back up. So to do that, we need more gas molecules in that bigger area. So it will shift to the side with more gas molecules. Again, that obviously is reaction dependent as to sort of which way it would go. Again, you're just going to look at the coefficients for anybody that has G next to it and add them together. So pressure and volume, I personally, like I said, think about it in terms of volume. It's keep it very simple. If I have a small volume, I need less gas molecules. If I have a larger volume, I need more gas molecules to fill it. And again, obviously, if you understand the relationship between pressure and volume, that's a good way. So if they say the pressure went up, you know that the volume went down, smaller area, less gas molecules. Pressure went down, volume goes up, more gas molecules to fill it. And again, that's just the simplest way to sort of think about it and figure it out. Question on pressure and volume. All right, so let's take a look at this one, and I'll just throw out some things here, and we'll talk about what's going to happen. So let's see here. Let's say let's see what happens if we add NH3, if we remove H2, if we increase the temperature, we'll say this delta H is, I'm just going to make up the number, positive 37 kilojoules. That is nowhere near the right answer. We'll go with, let's go with increase the volume. So see what you come up with here. Will this shift to the right? Left or no change? Okay, so let's take a look here and see what we got going. So if we have this system's at equilibrium and we do these things to it, first off here, we add some NH3. When we add some NH3, NH3 is on the right-hand side. When we add, it goes away from the side we added it to, so it should shift to the left there. Again, away from the side we added it to, since NH3 is on the right, it will shift to the left. Essentially what it's doing is when you add more NH3, you have a lot more products. That's going to, at a time, really make the reverse reaction kick off and go. Now, if we remove H2, so H2 is over here on our reactant side. When we remove something, we shift it towards the side, and that means this guy should also head in this direction. Again, when we remove the H2, we're removing reactants. That's also going to make really this guy kind of kick into gear to fix that sort of situation. Any question on those first two? Increasing the temperature. So when we're increasing the temperature, we do want, in this case, look at our delta H value, which I made up. And what we really want to look at is the sign of it. And we see that the sign is positive. So that implies that this is an endothermic reaction. And that means if we put the heat and energy into the equation, heat would be a reactant in this case. And if I increase the temperature, that would be like adding more heat, which is a more reactant in this case. And that should cause it to shift away from it. So it could go to the product side in this particular case. Questions on that one there? Now, lastly, we do have volume, and volume is related to pressure. So if we increase the volume, pressure should go down. But more importantly, we could just really look at the volume part of it. So since the volume goes up, we have a bigger volume, we need more gas molecules in that case. So when we look at this reaction here, there's 4 gas molecules on the left-hand side, and there is 2 gas molecules on the right-hand side. That means since we need more gas molecules, it is going to shift to the left in this particular case. Any questions on that there? So let's talk about this guy a little bit here before we continue on. So if I do increase the temperature, and since temperature really is the only thing that will affect the value of K, would we expect in this case the K value to increase or decrease? So take a second and think about it. Would you expect in this reaction, if we increase the temperature, should the K value increase or decrease? Okay, so hopefully you worked through it and you thought about it. So first off, we already established that when we increase the temperature in this reaction, it is going to shift the equilibrium to the right, to the product side. And since K is basically products over reactants, that means I should be making more products, which means the number on top should be a larger number than the number on the bottom, which then should give me an increase in the K value in this case. Again, K, the temperature being the only thing that will affect the actual value of it. And since it is in this particular example, heading to the right, we should expect more products to be made. More products means that when I do K, that's products over reactants, that should give me a larger number on top than bottom, and that should increase the K value. Questions on that there?
I'm sorry, did you say increase the K value, or did you say it's like the K value will increase, or we should increase it?
The K value in this case will increase if you increase the temperature, and it will increase from what it was at the original temperature. You know, the difference between the original temperature and where it ended up. The actual K value will increase, yeah. And again, just mathematically thinking about it, because it should shift to the right in this case, that gives us more products. And just mathematically speaking, we will have a greater ratio of products to reactants in that case when we do change the temperature. And again, that's because we change the temperature, everybody gains more energy. So when it does hit equilibrium, it will actually hit equilibrium at a different ratio, say at 50 degrees, than it would at, say, 25 degrees. But once we sort of raise the temperature, if you keep the temperature at 50 degrees, for example, it will maintain that K value. Other questions on that? All right, and one thing that we didn't sort of talk about, but let's make sure we do, so let's do it here. And if we add a catalyst to this reaction, if we add a catalyst to this reaction, it will have no change. So when you add a catalyst to a reaction, it will have no change. It does not shift the equilibrium position one way or the other. It just basically gets you there quicker. So just like we talked about with catalyst, it will essentially just lower the activation energy. It will allow it to get to the other side quicker, but it does not change the actual value of the equilibrium constant, again, because you didn't change the temperature. So you're still going to end up with the same ratio of products to reactants. You'll just kind of get there quicker than you would without the catalyst. So that's a very common sort of no change answer. Another one is as well, if you have some type of gas situation, if you add something like a noble gas to it, noble gases are chemically inert, which means that they really won't participate very much. So if you add like a noble gas, that's again another thing that will sometimes not have an effect on the equilibrium. Question on any of those there? All right, let's see here. Let's see what we just did. Yeah, let's get through this. Let's take a look at this one here. And just for the fun of it, let's just say this is, we'll change it to, since we did that, let's do exothermic on this one. Let's change it around. We'll make believe. All right, let's say we, let's see here. Let us say we added O2. Let's say we removed NO. Let's say we increased the pressure. Let's say that we decreased the temperature. Let's say we added a catalyst to it. And let's say we removed N2. So we'll shift to the left, to the right. Will there be no change? See what you come up with. Okay, let's take a look here. So we are adding O2, and O2 is on our reactant side. So again, AA, add away. So it should shift to the right in this case. We're going to remove NO. So NO is on the product side. So when we remove it, it should shift towards the side we removed it from. So in this case, it would shift towards the product side. If we increase the pressure, again, pressure and volume are related to each other. That means that the volume should go down. And again, in a small area, I want less gas molecules. So if I look on the reactant side here, I got a grand total of 2 gas molecules. And if I look on the product side, I got a grand total of 2 gas molecules. That is what we call a tie here. There is no higher side, lower side. So this would then be a no change situation. Again, there is no more gas molecules or less. So basically nothing much is going to happen in terms of that. Question on that one there. All right, so now that I changed this guy from endothermic to exothermic, so now that I made it exothermic, that means that when we look at the reaction, heat would be considered a product because I made it exothermic. And in that case, we're going to decrease the temperature. So temperature works the same way as concentration. We're essentially removing heat and energy from the product side. That means it should shift towards the product side, and we would expect it to shift to the right in this particular case. Now, talking about our K value, what will happen with our K value? Will it increase or decrease in this case? And again, in this case, since it is going to be shifting to the product side, we should be making more products, which means we should have more products over reactants. So top numbers should be larger. That means we should expect it to also increase in this case, the value of K from the lower temperature, from the higher temperature to the lower temperature in this particular case. Now, adding a catalyst, again, will not have a change either. And lastly here, removing N2, so N2 being a reactant. So when we remove it, it should come towards the side we removed it from, and it should go to the left in this case. Any questions on Le Chatelier's principle? Obviously, you need to figure out left, right, no change, all those kind of things. And again, as we've seen here, all the other changes, if you will, or stresses will not have an effect on the actual value of the equilibrium constant. So the equilibrium constant value will not change. The only one that it changes with, again, is the temperature. And that's because you're either increasing the energy or decreasing the energy. And that's going to allow a different ratio when it reaches equilibrium in comparison of two different temperatures.
Okay. Yeah. So why is removed NO go to the right?
Why is removed which one? I'm sorry?
Removed nitrogen oxide.
When we remove nitrogen oxide, it goes to the right. So when we remove something, it will shift to the side it was removed from. So basically what happens, what's happening here is when we remove this guy, we're basically kind of depleting this side, right? It's making it deficient. And what that's going to really do is going to really jumpstart the forward reaction to happen. And the forward reaction basically will be jump-started, and we will see some more products to kind of fix that, if you want to think about it that way. Like you got the product side, and then all of a sudden you got rid of some of the product side. So to fix it, this guy's going to head towards the product side to kind of fill it back in. And that's sort of what happens in that sense. It basically, by removing the products, we're really initiating that forward reaction to start to happen to kind of replace those products and kind of get it back to an equilibrium state.
Okay.
Other questions? Okay, that should wrap chapter 13, it is. And that also is the last chapter on the first exam, which is 1 week from Thursday. So 1 week from Thursday, we'll have our first exam on chapters 12 and 13. Any questions on that there? Okay, we're going to get into the next chapter, which is 14. Again, the notes are up on Canvas if you need it. Just give me a second to kind of rearrange some things here. Okay, that should do it. Okay, so this is chapter 14, which again will be on exam number 2. So again, not going to be on the exam next week. So sort of new stuff. So chapter 14 has a lot of stuff in it. So we're going to talk about a lot of things in chapter 14. And this is sort of the chapter that gives people a tremendous amount of problems, especially later on in this chapter. This is the chapter that does contain a lot of the topics where you really do need to understand what's going on in order to do the correct math. If you really don't have a good understanding of sort of conceptually what's happening in the problem, you're going to be in a lot of trouble because you're going to try to do math and there's going to be plenty of numbers for you to do the math, but it'll be completely wrong because that's not even what's going on in this type of problem. So out of all the chapters, this one and the next one is usually the two that gives people sort of the most difficulty, but definitely towards the end of this one, you really do have to sort of really understand sort of what's happening. You can't just blindly put numbers into formulas because, like I said, you will get it sort of wrong a lot of the times. But we're going to start with a little bit easier part of this chapter, which is acids and bases. So let's talk just a little bit about sort of acids and bases. Acids, they have a sour taste. You shouldn't really taste an acid or a base if you're really in a chemistry lab. But things like vinegars, acetic acid, there's obviously citric acid. Acids typically will react with metals to produce hydrogen gases in a reaction you should be familiar with from Chem 50, which is a single replacement reaction. So if you take something like zinc metal and some hydrochloric acid, the zinc metal will come in and kick out the hydrogen, and that'll give you some zinc chloride plus some hydrogen gas that's being produced in this particular reaction. And again, that is a single replacement reaction where whatever is coming in is more reactive than when it's replacing. Acids also react with carbonates and bicarbonates to produce carbon dioxide in another type of reaction that you should be familiar with as well. So, for example, take some hydrochloric acid and you react it with some sodium bicarbonate. You will get some sodium chloride and some carbonic acid. And as you may be aware of, this is a double displacement reaction followed by a decomposition reaction where that breaks apart into H2O and the CO2 gas that gets generated is the decomposition of your carbonic acid. So that's a very common sort of reaction that takes place. Bases, on the other hand, by the way, acids turn litmus paper red. So usually if you have red litmus paper and it turns, blue litmus paper and it turns red, it usually means that it's acidic. So blue litmus paper that turns red will mean that usually the solution is acidic. Bases, on the other hand, have a bitter taste. Again, shouldn't be tasting bases. They also feel very slippery. A lot of soaps are bases. Drain cleaner are bases as well. So those are common sort of characteristics in terms of bases. they are the ones that take red litmus paper and they turn it blue. Yeah? So red litmus paper turns it blue means that it is going to be basic, or sometimes basic means alkaline. Yeah, is another term for it. So somebody says make it alkaline, it means they're trying to make something basic. In addition, acids, you should be familiar with the nomenclature of acids from Chem 50. You should know what their names are. Just a really quick review, just in case when you talk about acids. When we talk about the names of acid, it really involves whether or not it has oxygen. So if it is no with the oxygen, it is hydro something ic acid. So like HCl, hydrochloric acid, no oxygen. HBr, hydrobromic acid. Again, no oxygen there. Also, when we do write acids, it typically has the aqueous symbol next to it. That implies it's a water environment. That's why we don't call this hydrogen chloride or anything like that, or hydrogen bromide. Again, that aqueous is important when you do that. If it does have an oxygen, it will either have a polyatomic ion that ends in 8, which means your acid name will end in ic acid. So like HNO3. NO3 is nitrate ATE, that is nitric acid. And it may end in ITE, the polyatomic ion, which means if it does, then it's OUS acid. So if you take something like HNO2, NO2 is nitrite, this becomes nitrous acid. So again, that's something you should have learned in Chem 50, so you know how to properly name these guys and write the formulas for these guys here. Questions on nomenclature here. Okay. So then let's get to acids and bases. So sort of an early definition of acids and bases was one that was made by Arrhenius, the the guy that we saw there in kinetics. And basically he said that any substance that basically can produce H plus or H3O plus in water is considered an acid. And in acid-base chemistry, H plus, which is the hydrogen ion, and H3O plus, which is a polyatomic ion, which is known as the hydronium ion, they are essentially equal to each other. They are interchangeable. They are used interchangeable, H plus and H3O plus, basically to represent an acid or acidic type conditions. And they're interchangeable both in the reaction and both in a formula as well. So I'm personally going to probably use H plus most of the time. So anywhere I kind of put H plus, you can substitute H3O plus, just kind of what I usually use. So it's basically the same. And the real difference is why you get one versus the other is you could actually see it in this reaction here. This is hydrochloric acid and water. And basically when it goes into water, it's going to make H3O plus and Cl minus. You can just as much write the same reaction as HCl, breaking apart into H plus and Cl minus. So these are sort of equivalent reactions. The difference is if you include the water in the equation, that is when you're going to get the H3O plus. If you eliminate the water, which is very commonly done with acids, you will get just H plus. So it's the same deal, same exact reaction. Again, most people, a lot of times when they write the reaction for an acid, just dissociating or breaking apart in water, they usually will leave out the water in the equation, and then they will just get H plus on the product side. If you want to leave the water into that reaction, perfectly fine. You will just get H3O plus at the end. They both, again, represent the exact same thing. So that's a very common thing that you'll see a lot of in this chapter. And like I said before, I personally will probably use H plus most of the time. But again, anywhere I put H plus in an equation or put it into a formula, you could substitute out the H3O plus. So basically anything that's able to generate H plus basically on the product side is considered an acid, and a base is anything that can produce hydroxide ion in water. So here NH3 reacting with water produces our hydroxide, again going to be a base. One important thing, I'll say it now and we'll probably say it a lot as we go through this chapter. Oftentimes people really struggle with the idea of, is it an acid? Is it a base? Should I be thinking of this as sort of an acid or a base? And the really simple way to sort of think about it is you should look on the product side of your reaction. And if you see H plus or H3O plus, it is going to be an acidic type condition. If you see OH minus on the product side of your reaction, you're going to see OH minus on the product side is going to be probably basic. And that also brings up another very important part of this chapter where people extremely struggle is writing these equations. So you need to be able to write these equations properly so that when you look at them, you have that information available to you. So people oftentimes struggle a lot in the writing the equation part. And it's really important because if you could get that equation down correctly, hopefully it gives you a lot of information about what's going on. And that information is very useful when you go to the calculation part to allow you to do sort of the right calculations. So, you know, as weird as it may sound, you know, you think, well, the equation might not be that important in this thing. I just need to kind of get the right formula or think about the right thing to do. It really is important to make sure that you write them correctly. I can't tell you how many times as we go through a chapter like this that I've seen people write an equation and then for like an acid type condition, and they just write it like basic or basic, and they write it an acid type thing. And again, it really just hinders the whole calculation. So sort of a really early definition of acid and bases was this one, just sort of a simple, something that produces H plus in solution or something that produces OH minus is an acid or a base. His real work was sort of limited by the idea that he did focus in a lot on bases that just involved hydroxide. And a more sort of general definition of acid and bases then came about. And this is the Bronsted-Lowry definition. I'm not sure where Lowry went to there. So the Bronsted-Lowry definition of acid and bases. A Bronsted-Lowry acid is a proton donor. So a proton is an H plus. It is called a proton because, as you also know, hopefully from Chem 50, that hydrogen has one proton, one electron, and no neutrons. That means in order for it to become positively charged, it had to lose an electron, and then it became H plus. So H plus also very common in addition to becoming the hydrogen ion. So it's called a proton here in acid-base chemistry. So a Bronsted-Lowry acid is something that will give away an H plus, not just the H, but the plus is important as well. And a Bronsted-Lowry base is a proton acceptor. So that is something that will accept an H plus. So our acid giving away the H plus and our base accepting the H plus. And when we do so in sort of the Bronsted-Lowry condition, basically what's going to happen here is our water is going to act as the acid, is going to donate its H plus over. When it does, it creates NH4 plus, and when water loses the H plus, it makes OH minus. And in a Bronsted-Lowry condition, we get what are referred to as pairs. So we get acid conjugate base pairs or base conjugate acid pairs. And the relationship is this: the acid on one side is related to the conjugate. Let me draw that arrow right there. Laid up too soon. Come back, try that again. The acid on one side is related to the conjugate base on the other side, and H2O and OH minus are related to each other, while the base on one side is related to the conjugate acid on the other side. And the difference between these, if you look at the difference, between NH3 and NH4 plus, it is one more H plus, while the difference between H2O and OH minus is 1 less H plus. And that is an important thing for an acid conjugate base pair. The only difference between those two things can be 1 H plus. So just 1 H plus only can be the difference between those two things in order for them to be conjugate acid base pairs. If you have more than 1 H plus difference, they are not pairs. If you have some other element in addition, they are not pairs. The only difference can be 1 H plus. Also important when you look at an equation such as this, it is always on the reactant side where you find your just plain old bases and acids. And it's always on the product side where you find your conjugate acids and your conjugate bases. So your conjugate acids and conjugate bases on the product side, acid and base, regular acid and base on the reactant side. Again, the only difference should be 1 H plus difference between them. And again, that's because the definition here is somebody donating and accepting 1 H plus. Question on that there. All right, so why don't you take a second here, look through these and determine which one of these guys are, or which ones of these are acid conjugate base pairs. Okay, so let's take a look here. So looking at the first one, the difference here between HCl and OCl minus is 1 H plus difference, but it's also an O difference, right? This guy's got an oxygen, this one does not. So these guys would not be a pair because of that. It's more than just a 1 H plus difference. Looking at the next one, which is H2SO4 and SO4 2 minus, these two guys are not either. That is 2 H pluses difference. So that is too many H pluses. So those guys are not an acid conjugate base pair. Looking at number 3, we have NH4 plus and NH3. Again, the difference between these two is 1H plus, actually. So number 3 looks like a winner. And number 4, difference between these is 2H pluses. So this would not be, and obviously 5 would not be. So it looks like number 3 there is the only one that is. Now you may say to yourself, aren't these guys related to each other? And they are related to each other, but they are not pairs. So a pair can only be 1H plus. And that is because the H pluses actually come off an acid one at a time. So what happens is H2SO4 loses that H plus and makes HSO4 minus. Then the HSO4 minus drops off that H plus and makes SO4 2 minus. So in terms of pairs, in this particular case, this guy and this guy would be pairs, as the only difference is 1H plus. This guy and this guy would be pairs, as the only difference between these two is 1H plus. But going directly from here to here, they are not pairs. They are like one step removed from each other. So they are not pairs because of that. So when you have something that's like a diprotic acid like that or a triprotic acid, the H's do come off one at a time. And again, the only difference needs to be just the 1H plus. Questions on that there? Okay, we will wrap it up there for today for lecture. Again, we have lab at 11:30. We're continuing the same experiment as last week. You also should have a lab report that's due as well, so make sure you get that in. And I'll see everybody in about 20 minutes or so in the lab lecture.